All right, everyone, grab a seat. We're going to get started now. Your first talk is by Alex Gaynor and is called Fast Python, Slow Python.
Hi, everybody. I'm Alex, and thank you for coming. So, quick bit about me. I write a bunch of open source software, mostly in Python. I try to give back to the community, and I work at Rackspace, to whom I'm very grateful for sending me here. And I'm very passionate about all of that, but I'm not here to talk about most of it. And if you want to talk to me about it, please find me later. This is, in fact, a talk about two things. It's to talk about performance, and it's to talk about Python. And it's about the intersection of these two. So first, what is performance? Whenever I give a talk, I like to define what I'm going to talk about. Performance is how fast a thing goes. I don't promise good definitions. Why do we care about performance? Performance sells. Studies from Amazon, Google, and other companies showed that when our websites are faster, we're more likely to interact and even buy things from websites. And second, it's the source of countless myths about what we can and can't do with Python and what is and isn't possible, and I really enjoy breaking those down. So, benchmarks are full of lies. You've probably read someone, maybe even me, saying things like, PyPy is 5 times faster than CPython, or Java is 20% slower than C. Postgres is 20 times faster than Redis. Unfortunately, these are largely nonsense. It's really appealing to try to condense a complex truth about how fast something is into a single number. It makes it easier for us to reason about what tools we want to use, and it makes it easier for us to communicate these to other people. But it's almost always a myth or a lie, or just a grotesque misuse of statistics. Performance is about specialization. This means two things for us. First, it means that any benchmark that doesn't look like exactly the application we're trying to understand the performance of will lead us astray. If we try to understand the performance of a big system by looking at a little system, we'll often be misled. Second, it means we can achieve performance in our own applications by specializing, either by changing the way we write software or by making our tools do specialization for us. In testing, we like to talk about the idea of integration versus unit testing. Similarly, we sometimes talk about the idea of micro or macro benchmarks. What we don't talk about is the differences between micro and macro benchmarks, the way we talk about integration versus unit testing. We know that unit testing makes it easier to test little parts of our code and test complex paths between them, but integration testing lets us understand that the full system works. What are the differences between micro and macro benchmarking? And when we make claims like Java is 10 times faster than Python, what are we talking about? It turns out most of those claims come from tiny little micro benchmarks running over a single small loop. And then we try to extrapolate from those into, hey, I can't put Python into production. My web server will serve 10 times less requests. But we know that's a myth. There's an incredible story from a number of years ago where someone benchmarked Ruby on Rails versus a Java web application, coming in with the hypothesis that Java is so fast, they've put so much energy into optimizing it, surely it'll be faster. And it ended up being that the Ruby on Rails application was faster. Why? The Java application was repeatedly reparsing some XML over and over and over again. We're really bad at extrapolating. So that's performance. What is Python? Python is the language that we all know when we type Python. But importantly, for most of this talk, I'm going to try to be really precise when I say Python versus CPython. Even though what we get when we type Python most of the time is CPython, there's different things. Python is an abstract language for which we can build dozens of different machines that execute code in the exact same way. CPython is a specific machine, and it is what we get when we type Python most of the time. Python also isn't a few things. It's not Cython, it's not C, it's not Numba, it's not RPython, it's not the CPython C extension API. I'm not talking about the way we integrate Python with other systems, or when we use subsets of Python that are specially compiled like RPython or Shedskin or Cython. They're perfectly interesting, and they're perfectly valid, and they're very great for a wide variety of use cases, and they can often make our applications faster. But the one thing they can't do is make Python code faster. It seems to me it's truly impossible to make Python code faster by writing code in a different programming language. So everybody knows Python's slow. We're done. Python's slow. Dynamic languages are slow. It's impossible to fix, and everybody knows it. We have dynamic typing. The compiler can't know the types of our variables. Therefore, none of the optimizations we read about in classic texts like the Dragon book apply. This is nonsense. It's something so many people take for granted as an absolute truth, but it's untrue. Optimizing dynamic languages is truly different from optimizing a statically typed language, and it's true, most of what you read in the Dragon book absolutely doesn't apply. But for something like 30 years, we've been perfecting the technology on how to optimize dynamically typed languages, and we have all sorts of great tools for letting the compiler understand what your types are at runtime just from running your code without you needing to tell the compiler anything. We know that in Python, like many dynamically typed languages, you can monkey patch things all the time. You can change what a class is, you can change what its methods are, you can change what a global variable is. Anything is up for change almost at any time. How could you ever optimize under those constraints, with the possibility that the world might change under your feet at any moment? Again, this is a solved problem. We can make assumptions about what our code does, and what is being monkey patched and what isn't, and then we can do very cheap checks to make sure that our assumptions hold without changing the behavior of our programs, but simply making them faster. There is a lot of tension, I think, between our understanding of what it means for something to be slow versus something to be harder to optimize. Slow is a property of what happens when we try to run a program. I tried to run this program and it was slow. Harder to optimize is sort of an existential statement about the program itself. And it's true, sometimes we'll run Python programs with Python and they'll be slow. And it's true, we'll have to optimize them differently than the way we're used to if we've been reading classic compiler literature. But they're not hard to optimize. Our optimizations might not look like they came out of a textbook, but they are basically solved problems at this point. I've mentioned PyPy and the idea of these compilers a few times, so what is PyPy? PyPy is an implementation of Python. You run it and you get some Python. It usually runs your Python code faster, as a matter of fact, and that's why it's of particular interest to this talk. How? PyPy is all about specialization. It takes at your code and looks at what happens when it runs, and tries to specialize based on what code is running, what types are being passed around, and basically what's going on with your program. When CPython, what you get on most systems when you type Python, executes your code, it executes it very statically. It doesn't try to adapt to what's going on in your program or try to optimize based on what it sees. PyPy does, it specializes these things dynamically, and that makes it interesting to us, given that we've understood that performance is specialization. I want to offer you guys a deal. I said earlier, performance is about specialization. If you all specialize your code for the problems you're trying to solve, I'll specialize the code you're writing for the machine it's executing on. In other words, you choose good algorithms, and I'll make them run fast. I hope that sounds like a fair deal. So how can we go about specializing our code? To understand what specialization means, let's take a look at C. C is fast. Everybody knows it. Super fast. It's basically just a DSL, a domain-specific language for assembly. And when you write code that close to the metal, it's always fast. How does that happen, and what does that mean? This is a simple piece of C code. It's a struct, which is sort of like a class in Python if you aren't familiar with C, except for it's defined to only ever have 3 fields. It's got an X, a Y, and a Z field, and they're all doubles, so 8-bit floating point number, or 8-byte floating point numbers. So unlike Python, we're statically declaring the types of things, we're declaring what fields a class has in advance, and so we know that this will only ever take 24 bytes. It's pretty great. Here's a pretty similar Python class. We also see it has 3 fields, and if our code always instantiates this point object with floats, we'll have the same idea of always having 3 floats. In reality, it's a bit different in a few obvious ways. For one, we never actually declared the types of X, Y, and Z, and if we passed a list, a dict, and some random class we had, this method would work equally well. In fact, if we created a point object and then started adding random attributes to it later, that would also work perfectly well. We also know that these are always allocated by a garbage collector, so the patterns of passing these around and mutating them are different from what we might know if we know C. And of course that means there's some overhead, right? There's no way it could be equally fast when we're not declaring any of these details to C, where we laboriously detailed exactly what fields we had and exactly what types they had. I don't care. I don't care that it looks different. I don't care that it sounds super hard to optimize. We've done it. That's my responsibility in our deal. You've written code that accurately expresses the idea you want to have your code execute. I promise you we'll make it fast. And in fact, we have. Since 1988, we've known how to make code that works exactly like this fast. We have strategies for dealing with these problems, and we actually execute on our strategies reasonably well. Unfortunately, I often see code that looks a bit like this. It looks similar to our last example, right? We've got x, y, z. I told you they'll have floats. It will work even if they don't. How is it different? Well, here we're using a dict instead of writing a class. They look similar. We probably hear people saying all the time, well, dicts are just lightweight objects. In fact, they're really different. Dictionaries are not a replacement for classes. They're something different entirely. Dictionaries are mappings of arbitrary key objects to arbitrary values. An object, by contrast, has a fixed set of properties and behaviors. Python may not enforce that, but my experience is if you start treating an object like something different, or a dict like something different, it gets remarkably difficult to reason about your code. Plus, there's a giant performance difference between our understanding of these. Even if there wasn't a performance difference, I still think they are very conceptually different. But there is a performance difference. I was recently working with another team at my company on a code base, and they were having an issue where memory usage was exploding on certain requests. It was going up by 60 megabytes within the context of one request, and this was just obviously unacceptable to them to be wasting all this memory. So we started looking through the code, and we quickly found that all over the place, dictionaries were being used to represent what I thought of as objects, something we had an understanding of. For example, a ticket in a bug tracker was being represented as a dictionary of fields. When we changed these to be represented as objects, almost immediately we saw a drastic difference in the amount of memory used and the performance of the application. Dictionaries are not specialized. We have one dict type that represents any shape you can imagine, but we have different classes for different ideas within our application. Classes are specialized, dictionaries aren't, and they're specialized for different purposes. Dictionaries are really well specialized in Python for the idea of mapping things to other things, specifically arbitrary things to other things. And we'd like our Python runtime to be able to take advantage of these specializations for us. This is a C++ equivalent of that Python code. We have what C++ calls an unordered mapped, like a Python dict, which maps strings to doubles. Here we've said the types explicitly, even though in Python we didn't have to. It's got an x, y, and a z field. No one would write code like this in C++, even though we very often write similar code in Python. It looks a little ridiculous and unwieldy, partially because C++ is generally ridiculous and unwieldy. But also, if we ran this, we would find it super slow and doesn't accurately reflect the semantics of what we're trying to do. Why do we think this is ridiculous in C++ and acceptable in Python? My hypothesis is that it's because for a long time, for close to 20 years, on most implementations of Python, there was no performance difference between the dict version and the object version. As a result, we've developed an ethos that somehow dicts are more lightweight than objects, even though now we know that's untrue. And as a result, we have this recipe for slow code. On modern Python, such as Python 3.3 and above, or PyPy, we're able to take advantage of this specialization in what the ideas we're expressing. And the performance difference can be colossal. Here's another example. This is some code from the standard library, actually, in the UUID module. What idea are we trying to express? This function that this code is in takes 5 arguments, and you're allowed to pass exactly one of them. So it raises an error if not exactly 4 of them are none. All the arguments have defaults of none, so we're just making sure that only one value is passed. What is the algorithm being expressed in the program? Well, we're expressing the creation of a list with 5 items, storing those all, and then looping over that list to check which values are none. By comparison to the idea we thought we were expressing, this is very slow. Why did we write code this way in the first place? I imagine because it was a bit shorter. We really only took 1 line of code to express this idea. And probably no one was benchmarking, nobody cared about performance. And less typing is appealing. This is another classical case of code that's not specialized. Python will specialize it nicely for the machine. Count is super efficient, just goes through each item and then calls to check if the items are equal. But the actual algorithm we've written isn't specialized for the use case. List.count is a very general tool for checking how many items in a list are equal to something else. We're trying to express a more specialized idea, though. Here's another way of writing it. It's more specialized to our exact case. It's definitely more typing, takes 4 lines instead of 1. But here the code actually models the algorithm we're trying to express. We have 5 values, and we'd like to know how many are none. So we write 5 checks to see if a thing is none, and as a result, both on PyPy and CPython, we're able to get faster performance. Why did this happen? Again, I think looking to C gives us some knowledge. If we'd written this list.count version in C, it would look pretty ridiculous. This happens in C because it's outrageously verbose. Creating a list with a few items, there's probably no built-in count method on our container. This verbosity in C shines a light on how much we're abusing this list.count general construct for a very specialized purpose. As a result, we don't tend to write this kind of code in C. Python is not wildly verbose, and that's a fantastic thing. It really is. But it does mean that sometimes it's even easier to use a general tool than it is to use a specialized tool. And as a result, the use of the general tool doesn't stick out like a sore thumb. So let's talk about strings. Strings are probably the most common data type you could possibly imagine. We use them in practically every function we look at, and for many applications where Python is quite popular, they're really the center of our world. Here's a slightly frightening piece of C code whose objective is to read data from a file descriptor, remove any leading spaces, and then print the result out. It's super efficient. It only does one allocation, one call to malloc the entire time, and reuses this memory forever. Here's our equivalent Python code. It's much simpler, much easier to read, more correct, less likely to crash, and better in every way except for one. It's much slower. Instead of removing our allocation outside of the loop like we can do in C, Python doesn't really have faculties for us to do that, and so each iteration through the loop, we reallocate a new array to stick our data in. And then when we call lstrip to remove our leading spaces, we allocate another copy of this data. We can even imagine if we wanted to print not the exact data we had, but the lowercase version, where we'd call lower, and we do yet another copy, yet another allocation of our memory. This costs us performance. And it's unfortunate because what we've written is much better in so many ways. As a result of this, myself and David Reed wrote a library called ZeroBuffer. ZeroBuffer tries to take the ideas from C, but express them to Python in a sane, Pythonic, and performant way. Here's a piece of code written using ZeroBuffer that's impossible to write using what's available in Python. We create a buffer that's 8192 bytes, and then we read all the data in from a file. Then we split this buffer on colons and print out each component on its own line. The interesting thing is that where split in Python on a string creates a list with each element, and each of those string elements is a copy of all the data from the bigger string, here we return a view over the original data, meaning we don't do any copying. Further, we're able to not do any copying when we're reading our data in from the file, and we're able to not do any copying as we write the data out to standard out. This can give us some incredibly increased performance, and I think you'll find the result is almost as simple and almost as Pythonic as the original. And you can find all that code here. There's a few more myths I'd like to talk about. People often say function calls in Python are really expensive. If you care about performance, you should avoid those. Only use the built-in data types, because we know those are fast. Use tuples, use lists. Maybe don't create expensive things like objects. Those are slow. Don't write your Python in the same style as C or Java. The things you know from there to get fast code won't be the same as the things you write in Python. This is okay if you're trying to optimize your code for CPython, or maybe even just CPythons of the past. But if you don't, if you're willing to run on another Python, you'll find that following these types of advice gets you a very local maxima. And I fear it's going to help you write worse code. It might help you write faster code, but also worse code. So I advise you, please try running your code on PyPy first. One of the things that makes me really proud about my work on PyPy and the PyPy project as a whole is that we have a no excuses attitude. We don't think the excuses I talked about earlier are good enough, and we don't think any other excuses are good. We're not going to tell you to make your code worse to make it faster. Don't manually inline your function calls. That's our responsibility, and we wouldn't have it done any other ways. Like I've talked about in this talk, I'll suggest ways to make your code different. to specialize your code. But I hope you'll find that this advice is categorically different from other advice. There are okay ways to make things fast, and there's ways that aren't okay. I've talked a lot about conventions. Conventions of fast Python code, conventions of slow Python code. And it's clear that if we want to write really fast Python code, we have to take a little bit more care in the Python code we write. And this is, to me, a big challenge. Because amongst other things, we take pride in the fact that Python lets us put things together, write our code incredibly quickly, and ship applications much more easily than we would with other tools. And part of the reason we're able to ship our code so quickly is because we don't have to care about these details. We don't care about the exact memory allocation patterns, how much space a struct takes, or any of these other things. So again, I'll offer you a deal. You can be super casual when you write code whose performance doesn't matter. But if you're going to write a widely used library, pay a bit of attention. Don't dictate to your users that their Python code is slow. Because that's what we do. When we write a library that's slow and then tell other people to use it, it generates the feeling that Python code must be slow because all the libraries we have are slow. And please, when you write the super fast to ship but kind of slow prototype, when it's time to write the fast version, let's have a world where we can write the fast version of our application in Python just as well as we can write the slow version of our application in Python. I hate heuristics. I want us to have great APIs for writing high-performance Python in Python. Because otherwise, as a compiler author, I'm forced to look at patterns. And patterns means guessing. And I'm forced to come up with heuristics to try to understand what your code means, even though it's not what you wrote your code to do. And yeah, we can often get good performance by sort of guessing. I can see that maybe the way you use list.count only with a constant number of items in the list, I can specialize that for you. I can maybe figure that out. But one of the other things it results in is inconsistency. What if for whatever reason my algorithm wasn't able to see that you only ever had 5 items in that list? What if you reformatted the code slightly and called append, and now my optimization stopped working, even though you thought your code was expressing the exact same ideas? It's much preferable that we find ways to let our Python code say what we want it to say, instead of letting our Python code say what we think is the least way to type the fewest characters. I want us to take a lesson, of all places, from the Java community. Like most of us, most Java programmers spend most of their day happily prancing around, writing Java code, happy as the day. But sometimes they hunker down and they write serious, high-performance code. What language do they write it in? Java. So often in our community, when we need to sit down and write serious, high-performance code, we turn to other languages. We turn to C. We turn to Fortran. I want us to find ways to write serious, high-performance code in Python itself. Thank you. Questions?
All right, so for purposes of objects are faster, is that true of a named tuple?
It is an excellent question. A named tuple, since you create a new type of named tuple for every use case, has a similar property to creating your own class, in that it allows the interpreter to see, hey, I want to specialize on this set of fields in this type of object.
So Pyramid has a concept of view functions where you can return a dictionary that would, in some cases be turned into a JSON reply, or in some cases be passed to a template. And so do you think this is a good use of a dictionary, or maybe use some specialization here too?
Yeah, this is one of the fascinating cases that I think dynamic languages show us that most statically typed languages try to make us avoid thinking about, in that what we're specializing for depends on what perspective we have. From the perspective of the view author, yeah, I want to specialize. My use case, the algorithm I'm expressing, is about a template that has this form, and it has this author object. It's got these things. From the perspective of the template author, the template engine author, of course, it's like, hey, your template works on some context that's got some data in it. I think it would be better if we could specialize for the use case of the view function author but I understand how we've come to the conclusions we've come to in this case.
Thank you.
So I guess a bit more of a, I don't know, maybe not philosophical question, but like, so one of the things one of the common threads throughout this has been generally allocations and copies are what makes things slow.
Yeah.
And so, but then you look at like the world of like Clojure and functional languages, which are doing all sorts of like fancy things with immutable data, and they're like, mutable data is really bad. Like it can cause weird errors because like you're never sure if something changed from behind you, and it causes all sorts of terror when you thread, and so it's like good from a programming perspective because from an authorial perspective because it gets rid of a lot of that having to copy all the time. But at the same time, like modification, then like whenever you whenever you change a dict allocation, whenever you append to a list allocation, do you think that there's necessarily a conflict between the immutable data style of programming and between optimization, or do you think like you can use the immutable data style of programming with like allocation, minimization, and other ways to make things specialized?
I don't think they're mutually exclusive at all. In fact, I think they're really complementary. First, I like to think of allocations and copies in sort of two different ways. Ways that are necessary to express the algorithm I have, and things that sort of just happen. And the things that sort of just happen, I like to think, what are the ones that my tool can reasonably solve for me? So for example, when you add two integers together in Python, you're allocating a whole new integer object. And if we were to start thinking about this, we would probably say, wow, that's so inefficient. Like, that's so ridiculous. But we have tools that can solve these for us. And so I don't worry about them. It's reasonable for a tool to solve those for us, I think. On the other hand, there are cases like I showed where I think we've simply written code in a different style that's resulted in this excessive allocation. When we look at the patterns of immutability from Clojure and other functional languages, I don't think of it necessarily as, hey, this means I'm going to have to create new objects all the time. I think about it in terms of, first, it allows for the parallelization and ease in writing parallel algorithms, which provides performance from a different perspective. I also think about the fact that they've written incredibly specialized data structures to accommodate this use case. Things like Clojure's persistent hash map are really novel algorithms that allow us to have dictionary-like objects which are immutable, but without the incredible expense of copying all the time.
Thank you.
So you highlighted a couple of cases where our intuition about what is fast or slow in Python is either outdated or flat wrong.
Yeah.
And it seems like often people take an approach to performance analysis that is like an approach to cryptography, which is to say that's very hard and you should leave it to the experts. And I'm wondering if you have advice for people who are coming up in programming for tuning their intuition about what's actually fast or slow and getting better feedback loops than saying, oh, I read on a blog post somewhere that you should use dictionaries instead of objects.
Sure. It definitely takes a long time for our intuitions and the common wisdom to catch up with reality. Java had a reputation for being slow probably a decade after it was no longer true. I think the best things we can do in these cases is to build tools to help people understand the performance of their application. The standard library comes with cProfile, which does a pretty good job of letting us see at a function level which functions in our application can be slow. There's a great module on the Python package index called Line Profiler, which lets us see at a line-by-line level what's slow. The PyPy project has a tool called JIT Viewer, whose objective is to let you see what the JIT sees about your code overlaid with what your code is. So you can see a line of Python code overlaid with the Python bytecode that is executed, overlaid with the JIT's own representation of the code, overlaid with the machine code itself. It sounds a bit overwhelming, but these tools I found to be shockingly intuitive and can really provide, even just simply looking at it and see, hey, here's where the bulk of the instructions are. I didn't expect that. A level of knowledge about our code that we didn't have without it.
So, one thing, pardon. Clearly the microphone has a coughing problem. one of the great things, I don't know if it's great, that the Haskell community has that I found relatively unique among language communities is that out of the past couple years, many library authors have started annotating their documentation with the space and time complexity of every function in their libraries in order to help hint to consumers of the library about what kind of performance they can expect when using certain functions and certain types. Have you seen this kind of analysis being useful in figuring out how extremely dynamic languages behave?
Absolutely. Before any sort of the optimizations I talk about here, the optimization of your algorithm itself will almost always dominate the performance of what you're trying to do. There's a great page on the Python wiki which documents the time complexity of most of the methods on the built-in types in Python, talking about how append is O of 1 and insert is O of n and these types of ideas. And it's super good. I highly recommend people read that wiki page on the Python wiki. And if they're not familiar with this sort of notion of complexity of our algorithms, studying material like that. Justin Abrams gave a talk here at PyCon about sort of that type of CS material for people who don't have that type of background. And so if you're not familiar with that, I highly recommend catching that video. I would love for that to take off within the Python community. I would also love for us to really take advantage of the fact that writing more specialized data structures. We have a few things in the standard library, and they serve us quite well for almost every use case. But there's also other data structures that aren't present. Skip lists, trees, different types of heaps. I would love to see libraries like this gain more popularity on PyPI.
Great, thank you very much.
Hi, I was just confused in the difference of the performance between like the objects and the dicts that you were talking about when an instance of a class has the dunder dict in it. I mean, at least when you're not using slots.
Sure. So objects have under dict. How could they possibly have different performance from dicts? Why do you believe everything you see? Just because you see a thing that looks like a dict, why does it have to be a dict? Python is an incredibly dynamic, reflective language, and it shows us all about its internals. But sometimes this can mislead us. Specifically under PyPy, we expose a thing that looks like a dict, but a dict can be many things on PyPy, which have totally different representations. This is the unfortunate case of heuristics that I talked about, where you see that and you assume it must be like the other dicts because we haven't exposed a different detail. In fact, it's represented entirely differently using a notion called maps from a programming language called Self many years ago. There's other cases of this as well, of course. If we look at a module object, looking at globals, we see that those live in what looks like a dictionary, but they have a little different properties. Globals almost never change. We probably want to optimize on that. And in fact, PyPy does, and for years there have been patches around the tracker and other places to let CPython optimize based on this intuition that things rarely change, all without changing what it looks like to us, the Python programmer. It's unfortunate that the way things look is often not how they are, but I'm not sure how to reconcile 20 years of Python code that sometimes, rarely, depends on these details with a desire to make it more clear.
Okay.
That is a challenge, for sure. Thank you very much.
Thank you, Alex. The next talk is in 5 minutes. 5 minutes.
Did I go over?
No, you're great.
Wait, I thought there was supposed to be 10 minutes between talks.
It's fine.
Oh, yeah. Cool. Got my timing right after all. Yeah.